everyone, I am Engineer Kamran Khan and you are watching my YouTube channel Learners of Civil Engineering. Guys, today I will be discussing my lecture number 5 with you guys, which is related with the subject of foundation engineering. And the contents of today's lecture are footing subjected to concentric loadings and footing subjected to eccentric loadings, then different cases of the load eccentricities, and numerical problem will be solved on the topic of eccentricity of soil. Now guys, let me first discuss the case of footing subjected to concentric loading. So guys, when the center of the column and the center of the footing will be same, then in that case the footing will be said as subjected to concentric loading. In this condition, the pressure beneath the base of the foundation will be uniformly transferred to the subsoil. Like this is the load of the footing Q, and that is the area of the footing P into L, where B is the width of the footing and L is the length of the footing. So a uniform soil pressure Q, small q, is equal to load of the footing divided by the area of the footing will be transferred to the subsoil. Because there is no load eccentricity, so there will be no movement coming on the footing, and the resultant pressure that will be transferred or distributed inside the subsoil will be uniform. Now guys, let me discuss the case of eccentricity. When the center of the column and the center of the footing will not be same, then in that case the footing will be known as subjected to eccentric loading. Like in this diagram, you can see if this is the width of the footing and that is the center of the footing, so you can see load Q is acting at a distance small e from the center of the footing. This small e is known as the load eccentricity. Now this load eccentricity will create a movement in the footing as well, along with the vertical load. Okay, now this pressure will be maximum at one end and minimum at the other end when the eccentricity of the load will be less than b by 6, where b is the width of the footing. Okay, so if the eccentricity will lie in this limit, then on the side of the eccentricity of the footing there will be a maximum pressure. Like you can see in this diagram, the eccentric load is located on the right hand side of the footing. So on the right hand side of the footing we will be facing maximum pressure, and on the left hand side of the footing we will be facing minimum pressure due to this load eccentricity. So now you can see at each and every point of the footing the load distribution is not uniform as compared with the footing subjected to concentric loading. Now what is the value of this Q max and what is the value of this Q minimum? So when the eccentricity will be less than b by 6, then the maximum pressure on the extreme right hand side of the footing will be equal to capital Q divided by BL into 1 plus 6E divided by B, where Q is the load of the footing, B is the width of the footing, L is the length of the footing, E is the eccentricity of the load, and B is again the width of the footing. It will be minimum on the left hand side. What will be the magnitude? The magnitude will be Q by BL into 1 minus 6E divided by B. Now, if the eccentricity will be greater than B by 6, okay, that was the case when the eccentricity was less than B by 6. Now we are encountering a case when the eccentricity is greater than B by 6. In that case, on the side of the eccentric load, there will be a maximum pressure, positive maximum pressure, but there will be a negative pressure on the left hand side of the footing. Okay, this is a negative pressure coming over here. Now this negative pressure is basically creating the tension on the left hand side of the footing, and as you guys know that soil can resist compression but it cannot resist tension. So what will happen on the left hand side of the footing? On the left hand side of the footing will try to lift off from the soil, or vice versa, the footing will try to overturn. So eccentricity greater than B by 6 should be avoided at any cost. Now the maximum pressure in this case will be given by this equation, when the eccentricity will be greater than B by 6. 4Q divided by 3L into B minus 2E. Okay, so this eccentricity greater than B by 6 or L by 6 should be avoided.
Now guys, let us discuss a case of one-way eccentricity in which the load will be eccentric either in the x-axis or the y-axis of the footing. Now you can see that is the center line of the width axis and that is the center line of the length axis. This point is basically showing you the point of application of a column load which is off center from the x-axis or width axis, but it is located on the center line of the length axis. So in that case, we can call this as eccentric with respect to the width axis. So we will use the effective dimension only for the width axis as b minus 2e, and we will use the effective dimension for, and we will not use the effective dimension for the length axis. So this new area will be used for the calculation of the ultimate bearing capacity beneath the base of the foundation, which will be having a uniform soil pressure. Now guys, let us discuss a case of two-way eccentricity. Now you can see in this figure there are two moments my and mx coming on the foundation along with a column load. Okay. Now the reason for this clockwise movement is my and for this anti-clockwise movement is mx is this EB and EL. Now EB is the eccentricity of the load in the x direction and EL is the eccentricity of the load in the y direction. So this EL is causing a clockwise movement and this EB is causing an anti-clockwise movement on the footing due to the load eccentricities. So in that case, you will use the effective dimension for the width of the footing and as well as effective dimension for the length of the footing is 2e, that is L is minus 2e, because the eccentricity is there in both the directions. Now, as I have discussed with you in my previous slide, that if there will be concentric load coming on the base of the footing, then the pressure distribution beneath the base of the footing will be uniform. But if there will be an eccentric load coming on the footing, then there will be a non-uniform pressure distribution beneath the base of the foundation. So in order to calculate the ultimate or uniform bearing capacity under the foundation, we will select a new area, and this new area will transfer or develop a uniform solid pressure beneath the base of the footing, and this new area will be called as effective area. Now, how this effective area will be calculated in this particular slide, there is a detailed procedure for the effective area method. Like you can see, that is the width of the footing, and that is the center line of the footing. That is the point of application of a column load acted on the footing at a distance of E from the center line of the footing. Now, if this eccentricity will be there in the width direction only, then we will use the effective dimension for the width axis as b prime is equal to b minus 2e, and you will use the original dimension for the length axis because eccentricity will be there only in the width direction. Now, what is the meaning of this b prime used and n prime used? This b prime used and l prime used will be the value of the b prime and l prime that we will use in the analysis. Now, the value of b prime used will be minimum of b prime l prime, and the value of l prime will be maximum of b prime and l prime. Now, let's suppose if b prime value is equal to 7 feet and l prime value is equal to 5 feet. So in that case, we will reverse b prime with l prime and l prime with b prime, because b prime by definition is the minimum value between b prime and l prime. So in this case, minimum value is 5 feet. So our b prime used will be 5 feet and our l prime used will be 7 feet. Now, if the eccentricity will be there in the length direction, then you will use the original width for the effective width of the footing, and you will use the effective length is L minus 2e, and the value of b prime and l prime used will be the same. Now, if you will use Terzaghi analysis, in the equation of Terzaghi analysis for the square footing is Qu is equal to 1.3 Cnc plus Qn2 plus 0.4 V gamma n gamma. Now, in this particular equation, in the third term of the bearing capacity equation is having an involvement of B. So in the third term, you will use the effective dimension for the B. Rest C, NC, Q, NQ, gamma, N gamma will not change, and over there we will use their original values. Only a change will be there in the third term. Now, if you will use Meyerhof equation, then the equation of Meyerhof equation is CNC, FCS, FCD, FCI plus QNQ, FQS, FQD, FQI plus 0.5 D gamma, N gamma, F gamma S, F gamma D, F gamma I. Now, over here in the third term is having an environment of V. So over there you will use effective dimension for the B. In calculating the shape factors FCS, FQS and F gamma S, again you will use the effective dimension for the width as well as the effective dimension for the length as well. But while calculating the depth factors, we will use the original dimension of the width, but we will not use the effective dimensions of the width due to the following two reasons. Number one, depth factors is considering the depth of the foundation, in which there is no role of the geometry of the footing, like the width of the footing and the length of the footing. So that's why we are using the original V there. The other reason might be the conservation or the safety, because if you will come here, then that is the equation of the depth factor. 1 plus 2 tangent phi into 1 minus sin phi whole square df over v. So if you will use effective width as compared with the original width, then it will increase the value of the depth factors, and hence will increase the ultimate bearing capacity. So in order to involve more conservation or more safety in our design, we will use the original value of B while calculating the depth factors. So guys, this is how we will be done with the effective area method. Now let me solve a numerical problem on the effective area method. For the solve profile given below, determine the allowable bearing capacity. What is required? The Q allowable. An isolated rectangular footing of dimension 2 meter by 2.3 meter that is subjected to a vertical load of 425 kilonewton, a moment of 85 kilonewton meter, and the factor of safety is 3. Now you can see the depth of the footing is 1.5 meter, the width of the footing is 2.3 meter, a vertical load of 425 kilonewton, and a moment of 85 kilonewton meter. That is the soil profile above the base of the footing. Phi is 20 degrees, C is 35 kilonewton per meter square, gamma D is 16 kilonewton per cubic meter. That is the location of the groundwater table, which is there located at the base of the footing. Now the soil profile beneath the base of the footing is having these values. Phi is equal to 25 degrees, C is equal to 0, and gamma saturated is equal to 19 kilonewton per cubic meter. Now, as you guys know, that the allowable bearing capacity is having this equation. Q allowable is equal to ultimate bearing capacity reduced by adding some factor of safety. Now, the subfactor of safety given in the statement is equal to 3. So, now let us find QU. QU is equal to, by using the Merhart equation, CNC, FCS, FCD, FCI plus QNQ FQS, FQD, FQI plus 0.5 B gamma, N gamma, F gamma S, F gamma D, F gamma I. Now, as we are interested in the pressure distribution beneath the base of the footing, and if you will consider the beneath the base of the footing, the value of C is equal to 0. So the first term of the Teslak bearing capacity will be dismissed. We will only solve this equation for the second term and the third term. Okay. So now let me start with the first parameter of the second term of the Merhart bearing capacity equation, which is Q, which is known as the surcharge pressure. This surcharge pressure will be equal to gamma into the depth of the foundation, where gamma above the base of the foundation is having a value of 16 kilonewton per cubic meter, and the value of df is equal to 1.5 meter. So this will give me a value of surcharge pressure as equal to 24 kilonewton per meter square. Now, let me find the value of the eccentricity of the load which is causing this movement. Okay, so the value or the equation of movement is equal to E into Q, where Q is the equal to the load of the column multiplied with the eccentricity of the column load. So rearrange this equation, you will get E is equal to M over q, where q is m is equal to 85 and q is equal to 425. So this will give me an eccentricity value of 0.2 meter. Now let us select that whether this load is eccentric with respect to the x-axis or it is eccentric with respect to the y-axis. So let me just study this sign convention. That is a clockwise movement. Okay. So now if you will switch towards this slide, then the clockwise movement is caused by the eccentricity of the load which will be there in the length direction or the y-axis. So now we can say that this is load is eccentric with respect to the length direction. So we will reduce the length dimension by L minus 2e, which will give me a value of L dash is equal to 1.9 meter, and we will use the original B while dealing with B prime, which is equal to 2 meter. Now B prime use is basically minimum of B and L prime use is basically maximum of B and L. So minimum of B and L is how much? 1.9 meter. So the value of B prime use will be 1.9 meter and the value of L prime use will be 2 meter. Now let me find the effective area. The effective area will be the multiplication of the effective size dimension of the footing, like 1.9 multiplied by 2. So this will give me the value of the effective area, which will be having a uniform pressure beneath the base of the footing is equal to 3.8 meters square. Now water table at the base of the footing. Now you can see there is a water table beneath just at the base of the footing. So while calculating this, the pressure distribution in this zone, you will use the effective unit weight for the soil. So the effective unit weight for the soil is equal to gamma saturated minus gamma of water. Okay. So this will give me a value of 9 kilonewton per cubic meter as the value of gamma bar, which is known as the effective unit weight of the soil. Now, bearing capacity factor for phi angle equal to 25 degree is NC 20.72, NQ 10.66, and N gamma 10.88. For this, you can use those formulas of the bearing capacity factors, or you can use the table 3.33, which is given in the Bowles book. Now, shape factors. For the shape factors, I'm having this formula: FCS is equal to 1 plus B prime use divided by L prime used into NQ divided by NC. Now this FCS is not required because C is 0 and that is used in the first term of the bearing capacity, so just don't calculate this. Calculate for FQS and FKMIS. So for this I am having this formula 1 plus B prime divided by L prime into tangent of phi. That will give me this value 1.44, and F gamma s will be equal to 1 minus 0.4 into B prime by L prime. So this will give me a value of 0.62. Now while calculating the depth factors, I'm having this equation df by b, which the depth of the foundation is equal to 1.5 and the width of the foundation is 2. So this will give me a value of 0.75, which is less than 1. So if df over b will be less than 1, you will use the value of k is equal to d by b, and for d by b greater than 1, you will use the value of k as tangent inverse d by b, where k will be in radians. So the value of the depth factors will be equal to dq is equal to 1 plus 2 tangent phi into 1 minus sin phi whole square. Now as the value of df by b is less than 1, so the value of k will be equal to df by b. So solving this equation, we will get the value of FQB as 1.2 33, and the value of f gamma d is equal to 1 for all angle phi's. Now there is no need for the inclination factors because the foundation load is not inclined. So now substituting all shape factors, depth factors, surcharge pressure, and the effective unit rate into this particular equation, you will get the value of the ultimate bearing capacity is 512.87 kilonewton per meter square. So the equation for the allowable bearing capacity, which I have discussed with you in the start, is Q allowable will be equal to Qu divided by 3. So this will give me an allowable bearing capacity value of 170.95 kilonewton per meter square. So this is how we are dealing with the footing subjected to different types of eccentric loadings. I hope this video was useful for you. Kindly like and share this video and subscribe this channel, and also press the bell icon so that you will not miss any future videos. Thank you so much. God bless you.